We will be having our first recorded lecture, and we will be talking about cylinders and quadric surfaces. So first of all, we will know what is cylinder in geometry, in 3D. So cylinder in real time is really different than this one, because in 3D, a semicurve that can be traced on the plane and is projected along the axis is called cylinder, and it does not change along the axis, right? When we have this curve, it doesn't change, then we will determine this as cylinder. So if we have a parabola on the plane, we take that parabola and project it straight. The curve does not change as we go ahead along with direction axis. Now we talk about surface. This is something that is still traced, but as we move along the direction axis, it changes, right? So one of them changes in 3D and one doesn't change. Cylinder doesn't change in 3D and surface does change in 3D. Alright, so we have already looked to special types of surfaces. First one was planes and other one was spheres, right? So here we investigate two other types of surfaces, which is cylinders and quadric surfaces. In order to sketch the graph of surface, it is useful to determine the curves of intersection of the surface with planes parallel to the coordinate planes. Okay, let me tell you first one thing. These curves are called traces. Okay, so what is trace actually? Whenever we have different curves in our plane, these are called traces. All right, so now moving to the cylinder thing. A cylinder is surface that consists of all lines that might be called rulings that are parallel to a given line and pass through a given plane curve. So this is the proper definition of cylinders. Okay, here we have an example. It says that sketch the graph of the surface where z is equal to x square. So if you just have a look over here in the solution, it says, notice that the equation of the graph z is equal to x square. Alright, before this, I would like to give you one thing that is a key tip to determine whether the equation is about cylinders or surfaces. So first thing is, whenever the equation has two variables, right? Two variables, it would be cylinders. Since it's 3D, right? 3D means that we have three axes, we have three dimensions. But still, in 3D, when we have two variables, in 3D equation we have two variables, that means we are talking about cylinders. Okay, and another property of the cylinder is it has one variable, so that means two variables and one constant. So equations have only two variables. You have to keep this thing in mind. Alright, now you can see here on the screen it's z is equal to x square and y is missing, right? So it means that we are talking about cylinders because we are just mentioning two variables. We are not going to name y over. So it means that in equation when we have two variables, it will be a cylinder. Another key component is whenever we have that missing variable, it means that curve is going to be directed in that particular axis. Alright, suppose we don't have the y over here, our curve would be directed in the y-axis. So these are the properties, actually properties of our cylinders, right? Third one is another key factor. Curve does not change along the direction axis, as we just mentioned before. Alright, so when we talk about this particular example, you can see z is equal to x square, right? So we cannot see any kind of y over here. It means that we have to we just determine it that this is a cylindrical equation, and our direction of the equation would be, our direction of the curves would be in the y-axis, right? So it says that this means that any vertical plane with equation y is equal to k, which is parallel to the xz plane, intersects the graph in a curve with equation z is equal to x square. So these vertical traces are parabolas. As now we're going to see in the next slide, you can see in the figure 1, it shows how the graph is formed by taking the parabola z is equal to x square in the xz plane and moving it in the direction of the y-axis. Now you can see this is actually making xz plane, right? This equation is making an xz plane and it is moving in the direction of y-axis. That is what we talked about. Whenever we have the cylinder, that will be moving in this particular direction when we have that missing variable. So the graph is surface called a parabolic cylinder made up to infinitely many shifted copies of same parabola. Here the rulings of the cylinder are parallel to the y-axis. So the rulings are actually these lines. You might see these lines which are parallel to the y-axis. These are called rulings, right? So these are parallel to y-axis and these are making parabolas, and this parabola is in the direction of y-axis. All right, we have noticed that the variable y is missing from the equation in example 1, right? So this is typical of a surface whose rulings are parallel to one of the coordinate axes. So if one of the variables x, y or z is missing from the equation of a surface, then the surface is cylinder, right? As just I mentioned before, whenever we have that particular missing variable, any of them, x, y, z, any of them, it means that our cylinder gonna be move in that direction, that missing variable direction. So here you have to mind something, some factors. When you are dealing with the surfaces, it is important to recognize that an equation like x square plus y square is equal to 1 represents a cylinder and not a circle, right? It does not represent a circle but a cylinder. The trace of the cylinder x square plus y square is equal to 1 in the xy plane is circle with equations x square plus y square is equal to 1, where z is going to be equal to 0. So this was actually all about the cylinders. We just know the properties of the cylinders. First thing is it will have just two variables, right? Second thing is it will not change the direction. It will be directed in one variable. And third thing is curve does not change along the direction. The curves will not be changing along the direction. The curves will remain the same. If we have the parabola will be same. Okay, now we talk about quadric surfaces. A quadric surface is graph of the second degree equation in three variables, x, y, and z. The most general such equation ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j is equal to 0, where a, b, c up to j are constants, but translation and rotation it can be brought into one of the two standard forms, right? So here we can see the standard forms of this particular equation, which is ax squared plus by squared plus cz squared plus j is equal to 0, or ax squared plus by squared plus iz is equal to 0. So quadratic surfaces are the counterparts in 3 dimensions of the conic sections in plane, right? They are actually equivalent, understand? So it means that these surfaces are equivalent in 3 dimensions. All right, so I would like to mention one thing you have to remember whenever you are dealing with the quadric surfaces. You have to know that these are actually the graphs of second degree equations, right? Now we can see whenever we will have a quadric surface equation, there would be square on our components. If there is no square on the component, it means that it is not a quadric equation. So we have to have this squaring on the components. So use traces to sketch the quadric surface with equation x squared plus y squared by 9 plus z squared by 4 is equal to 1. Alright, now here you can see that we have this particular equation, right? And we have to sketch a quadric surface with the help of this equation. So first of all, if you just give it a try without without just looking at this solution part, because uh, I don't have any kind of method to remove the solution right now here, because I cannot play the transitions in my phone. I'm recording it from my phone. So if you can just hide it for yourself and give it a try by yourself, that would be great. All right, looking back to the solution. By substituting z is equal to 0, we find that the trace in the xy plane is x squared plus y squared by 9. See, we just simply multiplied our z, we just put the 0 on the place of z squared by 4, which was our third component, right? So what did we get? We get an equation x squared plus y squared by 9 is equal to 1. So in general, the horizontal trace in the plane z is equal to k, right? So you can see here x squared plus y squared by 9 is equal to 1 minus k squared by 4. So what did we do? We put our z is equal to k, right? And then we can see in the next two steps, we can see similarly the vertical traces are also ellipses, right? Y squared by 9 plus z squared by 4 is equal to 1. And then we are applying 1 minus k square, right? And if you see that our k has to be greater than -1 and should be less than 1. So x is equal to k, and over here we will see y is equal to k, and we will have our k is less than -3 and greater than 3, right? So in this way we will just try to plot these three values over here. Now you can see in the figure 4 that shows how drawing some traces indicates shape of the surface, right? You just mark those points and then join the graph, and you will see that it makes an ellipsoid. That's why it is called ellipsoid, because all of its traces are ellipses. You can see it clearly, all the traces becomes in the ellipsoid form. So it is symmetric with respect to each coordinate plane. This is a reflection of the fact that equation involves only even powers of x, y, and z. It seems like if we have any kind of odd power, it could be like 1 or 3 or 5 or something like that, it will not be coming in this shape, ellipsoidal shape. So guys, in this solution, in example number 4 solution, we see that we put x is equal to 0, right? And we get z is equal to y square, because we exclude, we just multiply, we make x 0, and when x is being multiplied with 4 or any of constant or any power, it means that it's 0. So our equation is going to be z is equal to y square. So the yz plane intersects the surface in a parabola. Okay, if we put x is equal to k, that's a constant, we get z is equal to y square plus 4k square. So what do? We are simply switching our k with x, right? This means that if we slice the graph with any plane parallel to the yz, we obtain a parabola that opens upward, right? Okay, similarly, if we replace our y with k, or if we say that y is equal to k, the trace is going to be z is equal to 4x squared plus k squared, which is again a parabola that opens upward, right? So it means that in this equation we got two curves that are parabolas and that are upward, two parabolas that are upward, right? All right, so now we put x is equal to we put z is equal to k, and we get the horizontal traces. Before, the previous two were vertical traces, right? Now we talk about the horizontal traces. So we put z is equal to k, and the equation comes like, 4x square plus y square is equal to k, which we recognize as a family of ellipses. So knowing the shapes of traces, we can sketch the graph in figure 5. Now you can see over here, it is making an elliptical paraboloid. An elliptical paraboloid, right? It is made up of two traces of parabolas and one horizontal trace of ellipses. So we have some properties for elliptical paraboloid. The first one is it has two variables, right? So it has two variables. Actually, it has three variables, right? And two variables are having the power 2 and one is having power 1. As you can see in the equation, if we see over here z is equal to 4x square plus 2 plus y square, it means that z has power 1 and x and y has square, that is power 2, right? So in this particular elliptical paraboloid, we have two traces that are parabolas and one is ellipsis. So we have to remember these properties of elliptic paraboloid, which will be helping us to determine the equation and the shape of elliptic paraboloid, right? Okay, now we move to the example 5. We move to the example 5. In example 5, it says sketch the surface z is equal to y square minus x square. Now you can see this equation is a bit different than previous two equations or previous two examples, because here we have a minus in our equation, right? In the last two examples, we didn't have the minus. We had the plus sign, we had the positive values, we didn't have any kind of negative value, but we in this particular example we have this minus sign and a negative value. So try to do it yourself, right? And then we see the answer or solution. All right, so we head towards the solution. I'm sorry guys, because I cannot hide the solution from you people. Still, I'll appreciate that if you do it on yourself, and then we'll be like, then you just try to cross check. And because I don't have any kind of technology or any kind of option in my screen recording that I can hide without animations or without because I cannot play it in the PowerPoint actually. So it's just being open as, I'd say, a PDF, right? So moving to the solution, the traces in the vertical planes x is equal to k are the parabolas. Z is equal to y square minus k square, which open upward. Oh, okay. The traces in y is equal to k are the parabolas. Z is equal to minus x square plus k square, which open downward. And the horizontal traces are y square minus x square is equal to k, a family of hyperbolas, right? So this is, it clearly indicates the three kind of curves. First one is a parabola that is opening upward. Second one is parabola that is opening downward. And third one is a horizontal trace, which is from the family of hyperbola, right? All right, let's make it clear with the diagrams. So we draw the families of traces in figure 6, and we show how the traces appear when placed in other correct planes in figure 7. All right, now we talked about x is equal to k, and it was z is equal to y square minus k square, and we can see there are parabolas, right? They are parabolas and they are opening upward. But when we see the traces in y, that is y is equal to k, or z is equal to minus x square plus k square, we can see there's again a parabola, but it is now opening downwards, right? Its mouth is towards the negative portion. It is opening downwards. But when we see, on the other hand, the traces in x is equal to k are y square minus x square is equal to k. These are actually from the family of hyperbolas, So vertical traces are parabolas, horizontal traces are hyperbolas. So all traces are labeled with the value of k. All right. So here's another kind of representation. You can see the traces in x, which is equal to k. You can see three traces, right? And they all are opening towards the positive portion. How to say, toward upwards. Whereas on the other hand, we see the traces in y is equal to k are facing downward, and then traces in the z is equal to k are hyperbolas. You can see these are in the form of hyperbola. So when we join all of these traces, what do we make? We make a hyperbolic paraboloid. Hyperbolic paraboloid, right? So it says in figure 8 we fit together the traces from figure 7 to form the surface z is equal to y square minus x square, a hyperbolic paraboloid. So notice the shape of the surface near the origin resembles that of saddle. Okay, now it says you can see over here, you can see near the origin, this shape clearly seems like a saddle. Saddle is a seat that is used to ride a horse, right? So it clearly resembles that saddle, and this is called hyperbolic paraboloid, right? So we have some sort of properties for the hyperbolic paraboloid. What does it have? In the equation of hyperbolic paraboloid, we have 2 degrees of two terms, right? We will have y square minus x square in our particular equation, then 1 degree of one term, that is z. Okay, then one trace is hyperbola, right? One trace is hyperbola and two traces are parabola. As you can see here, one trace is hyperbola, two traces, that would be better, yeah. So one trace is hyperbola. In the z we can see the traces, these are hyperbola, and in the x and y traces we can see these are parabolas, right? And it shows that axis is parallel to the degree 1 variable. So the axes are parallel to the degree 1, which is z. So these axes are parallel to the z axis. All right, guys, we have example number 6. And in this example, it says sketch the surface x squared by 4 plus y squared minus z squared by 4 is equal to 1. So give it a try yourself. That would be great. I appreciate that. Okay, we head towards the solution. As we see that the trace in any horizontal plane z is equal to k is the ellipse, right? So x squared by 4 plus y is equal to 1 is plus k squared by 4, because we have just shifted z squared by 4 to the right hand side and we have replaced the z with k, right? But the traces in the xz and yz planes are hyperbolas. Understand? So when y is equal to 0, it would be x squared by 4 minus minus z squared by 4 is equal to 1. And when x is equal to 0, it would be x squared minus z squared by 4 is equal to 1. So it seems that one of the traces would be ellipse and rest of the two traces would be hyperbolas. Okay, let's have a look in the graph. In figure 9, it says that the surface is called hyperboloid of one sheet. Now, why it is called hyperboloid of one sheet? Well, we can understand that it is forming a hyperbola, right? Okay, but what is this one sheet concept? This one sheet concept is it is in a concrete form. It is not in parts, because we have one more hyperboloid that is of two sheets, and in that particular form we will have a two different kind of two different sides would be separated. All right, so that is called hyperboloid of two sheets. This is called hyperboloid of one sheets, and we can see over here on the x-axis the value is 2 0 0. On the y, the value is 0, 1, 1, and then we can see that it is making a hyperbola and then an ellipsoid, two hyperbolas and one ellipsoid. That makes hyperboloid of one sheet, right? So the idea of using traces to draw surfaces employed in three-dimensional graphing software or computers, because it is a bit difficult to draw that. You will not get the same result, but yeah, you can have a try whenever you find the values of x, y, and z. You can just put those values in the xyz plane, and then you can join those points, and you will make some sort of how to say graph. But it might not be that clear that you will get from the graphing software. So in most such software, traces in the vertical planes x is equal to k and y is equal to k are drawn equally spaced values of k, and parts of the graph are eliminated using hidden line removal. So that is what we're talking about. It enhances the shape, it enhances the connectivity between those points and makes a fine shape. So actually we have six kinds of surfaces. Six kinds of surfaces. We can see the graphs of quadratic surfaces are ellipsoid, elliptic paraboloid, hyperbolic paraboloid, a cone, hyperboloid of one sheet, and hyperboloid of two sheets. So this is what I was talking about. Hyperboloid of two sheets. So hyperboloid of two sheets, like vertical traces, are hyperbolas, and the two minus signs indicate two sheets, right? So you can see the properties, you can see the equations and the shapes of these particular surfaces of quadric equations. So actually these graphs are being drawn from the computer, that's why they are so fine. But you can just give it a try. You can make a graph, you can join those points, you can make a graph, and it would be really great for your understanding. All right, people, so yeah, so that was all about today's class, and we can have a question and answer sessions. All right, people, so this was all about today's lecture, and this lecture was not so lengthy because I was just giving a try whether you are adapting the things or not. If it is difficult for you, we will be moving to the conventional online lecture system. But if you have feasibility with this one, we will be trying to adapt this one as well. So you can ask me the questions in our question and answer session that would be conducted right after this one. So please go through again this video, and if you have any question, you can just mark it down, and then we can discuss it. Okay, thank you so much for your patience and watching the video.